All right, today we're going to talk about the generalized determinant formula. Before I write down the formula, it's going to be crazy, but the formula is best experienced. So don't get too anxious or frazzled over the formula. We're going to experience it, and I'll give you some examples. So the general formula for the determinant is it's going to be a sum over all patterns of the signature, which I'll describe what that is in a second, times a product of entries of your matrix. So let's just go through what this is. This is a sum over all patterns. By patterns, I mean Sudoku-like patterns. Again, we'll experience what this is in just a second with a small example. This signature means plus or minus based upon the pattern. And this pi symbol means a product. And it's going to be a product of entries from the matrix. So the key takeaway from this formula is there is a formula for any size matrix. We can calculate the determinant. But this is not necessarily a formula you would want to use, and we'll get into that in a second. But let's go ahead and just experience the formula. All right, we're going to start with a simple 2x2 case of what it means to be a pattern or a Sudoku-like pattern, whether you're plus or you're minus, and what the product is. So we know for the 2x2 that if you take the determinant of A, B, C, D, we have the formula that's AD minus BC. Right? And for the 2x2 case, we have two patterns. We have two Sudoku-like patterns. Right? One of them is going to be the AD pattern. And here, when we mean a pattern or Sudoku-like pattern, it means that in every row and every column, there's exactly one entry that we've chosen. So in this case, AD, there's exactly one in the first column, that's A, one in the first row, that's A. And similarly, there's exactly one in the second row and one in the second column. So that's AD is one pattern, and there's another pattern, which is this BC pattern. And so what this says is we're going to have, for each pattern, we're going to multiply up all the ones that we've chosen. So in this case, we have AD, and in this case, we have BC. And we're going to either plus or minus them. We're going to add or subtract them, depending upon whether it has a positive diagonal or a negative diagonal. So here, this is going to be a positive diagonal. This orients positively with the main diagonal. In fact, it is the main diagonal. And this one is sloped or oriented the other way. So in some sense, we're counting the number of times we're flipping things around. So if you remember last time, there were some examples where the shape became flipped, which resulted in a negative determinant. Well, the negatives come from how many times you flip it. So this is going to be a plus right here. And this is going to be a minus on this side. So altogether, we get the same thing as before, AD minus BC. So that's how this works for a 2x2. So let's go up for a 3x3. Let's figure out what this equation, this formula means for a 3x3. And the determinant is going to be based on the diagonals here. We know this from the formula. Let's use a different color. This is the positive diagonals. So we have, for the positive diagonals, we have AEI minus BFG, plus BFG plus CDH. Those are the plus diagonals. And then for the minus ones, we have the ones oriented the other way. All right, so for the minus diagonals, we're going to have minus AFH minus BDI and minus CEG. So these come from the formula we did last time. That's the formula and how we do it. But how does that relate to the formula we just expressed now, the general formula? Well, it turns out for every single term, there's going to be a pattern. So let's go ahead and try to find out what those patterns are. All right, so there's going to be 6 patterns. So we're going to copy this 6 times. All right, so for the first pattern, we have the positive patterns. We have these ones. And unlike before, it's not clear whether these patterns are positive or negatively oriented. So what we're going to do is we're going to look at them pairwise. We're going to say, okay, how are the pairs oriented? So here we have 3 pairs. And in that case, they're all positively oriented. Those are 3 positively oriented ones. Now for the next one, this one's a little trickier because there's only 1 positive oriented one, but there's 2 negatively oriented ones. So we have 1 positive and 2 negatives. So altogether, this is going to give us a positive. Those 2 negatives cancel each other out. So in some sense, going back to the example last time, we're flipping things twice, which results in a positively signed area. And then here, the same thing is actually going to end up happening. We have 1 positive and 2 negatives. So that's why those ones right there are going to be the positive. This is going to give us a plus, and this together is going to give us a plus. Right, now we can go to the other patterns. The other patterns which are negatively oriented are these ones. And like before, we can check all the pairs and see whether they're positively or oriented, whether they're positive or negatively oriented patterns. So these are the negative ones right here. And we'll see that just like the first case, we're going to have 2 and 1 for some of these and all 3 for the other. Oops, that should be a minus. Minus is red. There we go. Minus and 2 pluses. So altogether, this is going to give us a minus. And likewise, this is going to give us a minus, and this is 3 minuses. So that's going to give us a minus. So this is why we have 6 terms, and 3 of them are positive and 3 of them are negative. It just depends on exactly the orientation of the patterns. Okay, so now how does this go to the 4x4 case? In the 4x4 case, we're going to just do this in an example. We're just going to do an example. We're not going to do it in general. So we want to compute the determinant of a nice matrix. This matrix is going to be a little sparse, meaning it has some zeros in it. And one thing I should caution you with is that we are not going to list out all the patterns. There are too many of them. So in fact, there's 24 total in this case. So for the 4x4, there's 24. And in general, there's going to be n factorial. So the number of patterns grows even more than exponential. So calculating the determinant with this formula is not something you explicitly want to do in every case. So instead, what we're going to do is we're going to think about which patterns are going to contribute to the total. So we're only going to seek to find the patterns that contribute. So we're going to find the patterns that contribute to the total. And by that, I mean which patterns give you a non-zero product. All right, so in some sense, in some literal sense, we're going to play Sudoku, where we want to find patterns that are non-zero and have exactly one entry in every row and one entry in every column. All right, so what we can just start with the first one. So we have to pick, right, that's the only entry in the first row. So when we pick a pattern, we have to pick that one. That's the only way to pick an entry in the first row that will be non-zero. So we pick that one. And similarly, we have to pick this one. If we try to pick any other patterns, we get a zero, which is not zero. It's not going to contribute to the total. All right, so now things get a little tricky. Is the next row is we have three choices. We could pick any of these three, except we've already picked. We can't pick those two on the ends for the third row because we've already picked something in those columns. So we have to pick this one. Right, and then for a similar reason, on the final row, we only have to have one choice. We have to pick this column for the final row. That one is forced. All right. So what we've deduced is that for this particular 4x4, there's exactly one pattern that's going to contribute to the total. No matter how hard we try, even if we listed them all out, there's going to be only one out of the 24 patterns that's going to contribute to the total. And we can then use that to calculate the determinant. So the determinant of our matrix, we're just going to look at this pattern that we found. And so we know that it's going to be equal to the product of that entry, of those entries, which is 2 times minus 1 times 2 times 1, which is minus 4. But keep in mind, it can be plus or minus. So it can be plus or minus minus 4. All right, so now we have to deduce whether it's going to be plus or whether it's going to be minus. So to do that, we're going to look at our pattern and look at all the pairs and see how many times it's oriented the negative way, or all the ways it's oriented. So this pattern has those entries, and they're oriented positively with the diagonal in those three cases, and negatively in the diagonal in those three cases. So altogether, this pattern is going to contribute 3 pluses and 3 minuses. But when we multiply those together, overall you get a minus. It's not the balance of them, it's the product. So if there's an odd number of minuses, you contribute a minus, and it's an even number, it's a plus. So now this plus or minus is going to be a plus. So altogether, our determinant is minus 4 or 4. So this is a way we can use the formula in general without necessarily listing out all the different possibilities. What's also really nice about this formula is that it leads very well to some additional properties of the determinant. right, so there's 4 of these that we're going to go through, and these are all properties to be able to calculate the determinant based upon other things that you know. So let's do the simplest one, but maybe the most counterintuitive one first. And that is the determinant of a scalar multiple of your matrix. So this was the running example we did last time. We looked at the determinant of 2, 0, 0, 2, and we got that that was 4. And we can do the same thing with a 3 by 3 diagonal of 2's. And that turned out to be 8. And so the punchline here is that the determinant, when you multiply the matrix by k, the determinant is going to multiply by k to the n times the determinant. And this n here is the size of your matrix. All right, so why is this true? Right, we could use the formula, but let's provide an intuitive geometric explanation first. So recall that here we have in the 3D case, right? If you have 3D, when you apply the matrix 2, 2, 2 on the diagonal, this is going to stretch it in each of the principal directions by a factor of 2. So it's going to stretch it by a factor of 2 in the x direction. It's going to stretch it by a factor of 2 in the y direction, and it's going to stretch it by a factor of 2 in the z direction. And so overall, this cube, this volume, is going to multiply by a factor of 8. So you multiply it by 2 on each side, and that's going to give you a total volume that's times 8. So each dimension that you stretch is going to affect an additional factor that multiplies the final volume. And so in general, you don't multiply just by 2, you're going to multiply by 2 for each dimension, which is why it's k to the n. To apply the formula here, you can pull out that k to the n 2. So we're going to multiply over all patterns of the signature of those patterns times the product. So this is very intimidating. That's why I encourage you not necessarily to memorize this, but to feel it and just intuitively understand it. But now this k is going to go right into here. So now for each pattern, we're going to multiply by k for each entry. So every entry itself is going to contribute an additional factor of k. So when you multiply a matrix by k, every entry is going to be multiplied by k in your pattern. So when you multiply every pattern together, when you multiply the entries of each pattern together, you're going to get n factors of k. One for each entry. And so you can, in some sense, pull out this k, but you have to have n factors of k. And what's left is exactly the determinant of the matrix. So that's both a geometric and algebraic explanation of that property. And again, it's a little unintuitive because most of the times in linear algebra, we would expect the k to come out and it to be able to distribute the k in and out of the function, but that's not true for the determinant. All right, so the next property is about transposes. So for the transpose, one thing that's not as clear, but if we have a pattern, for example, this pattern from our example from before, and we take the transpose of the matrix, that same pattern is going to occur. So this is the transpose. And that same pattern is going to occur. And in fact, in this particular case, it's going to occur in exactly the same position. And moreover, the orientations are all maintained. This even holds even if the pattern is not as symmetric. So for example, if we take a different pattern, and if we apply the transpose of this, that same pattern is going to occur, but now it's not in the same places. Right? This pattern is slightly different, but even though they're in different places, the orientations among all of them are still in the same direction. So there's a plus and a plus, there's another plus and another plus, yeah, another plus, another plus, and we have those negative ones, and also this final one right here. So all the orientations are the same. So since you're multiplying the same things with the same signs, this is going to be the exact same arithmetic. Exact same products with the same sign. So even if you take the transpose, you're going to end up with the same value. So the punchline here is the determinant of A is equal to the determinant of A transpose. All right. There's two more that are related. These ones should be fairly intuitive. One of them are products. So the punchline here is that if we take the determinant of A times B, that's equal to the determinant of B times the determinant of A. All right, I write the determinant of B first to emphasize that the matrix A times B, this means apply B, then apply A. Right? So for an example, if we start with a unit box, and then we're going to apply some transformation. Right, this has some expansion factor, which is the determinant right here. So in fact, the determinant here is -3. And then if we apply another transformation, say 2, 0, 0, 2, this just doubles everything in every dimension. This is now going to double every dimension. So it's going to lengthen each vector by a factor of 2. And so the determinant of this matrix is going to be 4. And so altogether, right, kind of eyeballing it, that's a pretty big transformed shape over there. This is the determinant of A times B. It's just going to be equal to minus 12. Right? And the minus just has to come from the orientation of the vectors. Don't mind the minus too much, but just know that this area should be 12 times what we started with. And that's the intuitive explanation. You can go through the formula too. It's a little more tricky with the formula, but intuitively we have that if you expand something by one factor and then apply a different matrix, the total expansion factor should just be the product of the two. So we can multiply determinants like this, which is pretty nice. And then finally, this leads us toward inverses. Let's make this big. So the punchline here is the determinant of A inverse is just equal to 1 over the determinant of A. All right, so there's two explanations for this. Let's just go through the algebraic explanation first. So we know the determinant of the identity matrix, the do-nothing matrix, so that means the expansion factor is 1. But on the other hand, this is equal to the determinant of A times A inverse, because A times A inverse is the identity. So this is equal to the determinant based on the product rule that we just discovered. This is the determinant of A times the determinant of A inverse. So altogether, we have that this has to be equal to 1. And now we're going to solve for this. So we're going to put this determinant on the other side. And when we do that, we get the determinant of A inverse is equal to 1 over the determinant of A. So that's an algebraic explanation using that product rule of the determinant. An algebraic explanation is that if we have a matrix, say the one we had before, so we're going to take the unit box and we're going to multiply that by 1, 2, 2, 1. Right? This expansion factor is 3. So this area right here should be 3 times the unit box. So this expansion factor is times 3. Well, to invert this process, to go back to where we started, we have to go back to where we started. Well, we have to multiply that area by the inverse of what we started with. Right? So in fact, we have to multiply this by 1/3 or minus 1/3 if we're keeping track of the signs. And then we get the unit box back. So the expansion factor is exactly the inverse of the original one to get the inverse. So that's the geometric explanation. So all these properties are really useful, not only to compute determinants of products of matrices and related matrices, but you can also combine them to create some nice novel facts. So just to recap for today, right, we have this generic formula right here that's very crazy. Right? You're not expected to memorize this, but you should know how to use this. Right? You should practice it with a few 4x4s and know how to apply it. And then know that there's these additional properties of the determinant down here, including if you scale it, you scale by k to the n, not k, it's k to the n. The transpose is equal to its matrix. That is, the determinant of the transpose is equal to the determinant of the original matrix. We also have the product works in a very intuitive way. And also, because of the products, the inverses work in also a very intuitive way as well.